Hello everyone, Mr. Linder here. Let's talk about capillary dynamics and edema that occurs in the human body. And edema would be essentially swelling that takes place in the human body. So what are capillary dynamics? Basically, capillary dynamics are the distribution of fluid between the blood plasma and the interstitial spaces of the body. And this distribution of fluid is in a state of dynamic equilibrium. The movement of fluid is based on essentially two types of pressure. What most textbooks call hydrostatic pressure and osmotic pressure. Now, in reality, when you see the term hydrostatic pressure, really we're talking about a hydraulic pressure. The term hydraulic pressure is actually referring to the pressure that is exerted on the walls of a vessel, whether it's static or not moving, or whether the fluid is moving. And since the cardiovascular is a closed system, we're really talking about a hydraulic pressure. But unfortunately, most books will refer to this as hydrostatic pressure rather than hydraulic pressure. So just understand that you're basically going to see both terminology, but we're really talking about a hydraulic pressure rather than a hydrostatic pressure in the cardiovascular system. So when we look at the two types of pressure, whether it's a hydraulic pressure or whether it's an osmotic pressure, we are concerned about the net filtration and the net absorption that takes place within the cardiovascular system. So what we'll see happening is as blood transitions through the arterial side, so as we move blood through the arterial system, we're going to reach capillaries. And so as the blood is flowing through the capillaries, what we really want to see is a net filtration, okay? So a movement of fluid out of the capillaries into the interstitial spaces, but then we want to have a net absorption on the venule side. So we want to see fluid moving back into the veins so that we don't create too much viscosity on the venule side, too much thickness of the blood, and therefore the blood wouldn't move. So if we pulled all of the fluid out on the arterial side and we didn't have a net absorption on the venule side, our blood would get too thick and then it wouldn't flow through the veins and return to the heart. So we need to have these capillary dynamics take place. We need to see a net filtration followed by a net absorption. So there's this essentially this transition of fluid movement where blood, where fluid is moving out on the arterial side and then it's coming in on the venule side. So what's moving fluid out on the arterial side? Well, what primarily moves the fluid out on the arterial side is going to be your blood pressure. So your blood pressure, or essentially your capillary hydrostatic pressure, that's going to be forcing fluid out on the arterial side. But also what's going to affect the movement of fluid on the arterial side is any sort of osmotic pressure that's in the interstitial space. So what's creating the osmotic pressure? So let's talk a little bit about osmotic pressure. Osmotic pressure is created by the dissolved solutes. So things that are dissolved in the fluids, so dissolved solutes. So most of your solutes are going to be within your blood plasma. So blood plasma is going to have most of your dissolved solutes, and the primary dissolved solute is going to be albumin. So albumin's going to be in your blood plasma, so we could put little dots inside the capillary here, right? We have dissolved solutes in there, most of it being albumin, and that's really what's drawing right water into the cardiovascular system. But out in the interstitial spaces, you can also have solutes. Okay? So whatever solutes are out in the interstitial spaces would be, in essence, drawing fluid towards it. generally speaking, there's not a lot of dissolved solutes in the interstitial spaces that's going to provide much movement of fluid out of the cardiovascular system. That can change and that can lead to edema, but predominantly there's not a lot of dissolved solutes out in the interstitial spaces. Most of your dissolved solutes are in the capillaries, but by definition, we call that the osmotic pressure. So the osmotic pressure is essentially the pressure that draws fluid towards something, right? So if you're drawing fluid back into the cardiovascular system, that's because of the osmotic pressure. If you're drawing fluid out of the cardiovascular system, that would be because of the osmotic pressure. So osmotic pressure is determined by the solutes that are dissolved in solution, and they would be drawing water towards them. The main solute difference between interstitial fluid and blood plasma would be the plasma proteins. And so the osmotic pressure is predominantly in the cardiovascular system. The higher number is going to be in the cardiovascular system, drawing water back into the capillaries. So to give this sort of an equational context and to give it numbers, we would look at something like this equation, where we have fluid, things that cause fluid to go out of the capillaries versus values that would cause fluid to come into the capillaries. So let's look at what these numbers represent. So let's look at P sub C. P sub C, your hydrostatic pressure, or what I said earlier, would be essentially your hydraulic pressure in the cardiovascular system. So that is in essence your blood pressure. So think of this hydraulic pressure or hydrostatic pressure as your blood pressure. And so that's going to influence fluid moving out. Okay, so that's this yellow on the diagram here, arrow going out of the capillaries. Okay, notice though that the arrows are getting smaller because as you move through the capillary, the pressure within the capillary is going to go down. Okay, so there's a loss of pressure as we move from the arterial side to the venule side. But your blood pressure is basically the primary number that is forcing fluid out of the cardiovascular system. Pi sub I. Pi sub I, and when you see pi, pi is your osmotic pressure. So we're using the Greek letter pi to represent osmotic pressure. So if it says P sub I, that represents the osmotic pressure in the interstitial fluid. Okay, so pi sub I is out here. Okay, any sort of solutes that are drawing water out of the cardiovascular system. Now, again, that's in essence, not an important value right now. Under normal homeostatic conditions, your interstitial solute number is not contributing much to the movement of fluid. So generally, we call pi sub I 0 in most calculations. But if you had extra solutes out in the interstitial spaces due to pathology, that could change your capillary dynamics. P sub I, pressure in the interstitial fluid, is any sort of pressure that's out in the tissue spaces due to fluid in the interstitial space. Okay, so this is any sort of hydrostatic pressure or hydraulic pressure in the interstitial fluid. And then pi sub P would be any sort of osmotic pressure in the cardiovascular system. So any osmotic pressure in your blood plasma, primarily due to albumin. And that's going to be a higher number, okay, because you have a lot of dissolved solutes in the capillary. So this is going to be any of the orange values here, any of these orange arrows that are drawing fluids back in. So if you were to look at this numerically, most of the formula is affected by blood pressure and it's affected by the osmotic pressure caused by albumin. Okay, so let's look at the formula and put some numbers in. Okay? So we have pressure in the cardiovascular system plus any osmotic solutes drawing fluid, okay? So this is going to be on the net filtration side, okay? We're talking about basically fluid going out versus fluid going in, right? We're going to subtract these numbers from each other. So interstitial pressure plus osmotic pressure in the cardiovascular system. So let's give these some numbers. What's a good number for capillary hydrostatic pressure? So let's say your capillary hydrostatic pressure is 37. And let's say your interstitial osmotic pressure is 0, because again, there's not very many solutes out there. Okay, so most of the fluid out is being driven by your blood pressure. And then we're going to subtract any sort of pressure that's in the interstitial space. So let's use a value of 1, because there's not a lot of pressure out in the interstitial spaces. And then what would be drawing water back in? That would be all of your albumins. Okay? So we'll give that a value of, say, 25 millimeters of mercury, drawing water back in. So on the filtration side, what we're trying to figure out is there more pressure that's pushing fluid out of the capillary versus anything drawing the water back into the cardiovascular system. So we've got fluid out at 37, and we've got fluid in at 26. And so we have 37 minus 26. So we are plus 11 millimeters of mercury. So using this formula on the filtration side, what we're showing is that there is a positive pressure forcing fluid out on the arterial side. So in essence, we get a net filtration. There are more values, right? Greater numbers, okay? Especially your blood pressure. There's a greater blood pressure than essentially osmotic pressure. And so we're able to push fluid out on the capillary side. Let's look at the same formula, but on the venule side and see why we get net absorption. So same formula, P sub C plus pi sub I, that represents our fluid out, minus P sub I plus pi sub P. That represents our fluid in, but let's look at different numbers, okay? As blood flows through the cardiovascular system, as blood is moving through the capillary network, your blood pressure is going to go down. So let's say our blood pressure is now 17. We're still using 0 as our interstitial fluid osmotic pressure because, again, there's very little solutes out in the interstitial space. So we're going to call that 0 for now. And then we're going to subtract our fluid in values. Okay? So what's a good number, again, for pressure in the interstitial space? Well, it's still only about a value of 1 because, again, there's not a lot of pressure in the interstitial space. But we still have our albumin, okay, because our proteins aren't escaping. So we're still going to have a value of 25 for our osmotic pressure of albumin. So now we have 17 minus 26. So that's going to give us a net value of negative 9 millimeters of mercury. So what we're saying is that there's actually now more pressure drawing fluid back in on the venule side with this negative 9 value. And so we're getting a net absorption. So on the arterial side, we got plus 11 using our formula. So that gave us net filtration. But on the venule side, we're getting minus 9. So that gives us net absorption. We're drawing fluids back in so that there's still water in the cardiovascular system, so we don't have too much of a viscosity on the venule side and blood can still flow back to the heart. So net filtration on the arterial side, net absorption on the venule side. You should notice, though, that the numbers are different. We got plus 11 on the net filtration side, minus 9 on the venule side. That means that there's actually more fluid on the arterial side going out then there is fluid going back in. So there actually is, right, a little bit extra water. That's why we saw that there is, right, a pressure in the interstitial fluid, not a high pressure, but there's still water, right, accumulating in the interstitial spaces. And so we need to do something with some of that excess water. And so where is that excess water going to go? Well, let's draw in another vessel here. Let's put some other vessels that are moving through our tissue spaces. And those other vessels are going to be lymphatic capillaries. So your lymphatic system is going to pick up extra fluids and then return that to the cardiovascular system. So even though there's a greater net filtration, we're going to pick up excess water in our lymphatic capillaries, and then we're going to take those back to the cardiovascular system. So we pick up extra fluid. So filtration is greater than absorption, but excess fluid in the interstitial spaces can be picked up by the lymphatic system and taken back to the cardiovascular system. So what would be some causes of edema? Now that we know a little bit about capillary dynamics, what are some of the causes of edema? And again, edema is swelling of the body. So one of the first things to consider would be obstruction of the lymphatic vessels. If there are cancerous cells in the lymphatic system, if parasites get into the lymphatic system and they grow and they block lymph flow, that's going to lead to swelling because those lymph vessels can't pick up the extra fluids. So when you have filarial type worms, nematode worms that can get into the lymphatic system, that can lead to obstruction of the vessels, and that can lead to edema. You may be familiar with the clinical pathology called elephantiasis. So elephantiasis is caused by mosquitoes transmitting these nematode worms that end up blocking the lymphatic system, and they're going to lead to a tremendous amount of swelling within the interstitial spaces. And so it would look something like this. So here we see this immense amount of swelling, right, throughout the interstitial spaces because of the worms blocking the lymphatic system. So that is elephantiasis. So that's one type of edema. You would have to treat this by killing those parasitic worms. So ivermectin, for example, would be an example of a treatment option to kill off those worms, fight the infection, and then get those lymph vessels moving fluid again. Another cause of edema would be an increase in your blood pressure. So an increase in your hydraulic pressure or hydrostatic pressure. So what we call an increase in your P sub C, okay? Increases in blood pressure. So anything that can lead to increases in net capillary filtration, where you're getting more fluid out into the interstitial spaces. So this could be caused by venous obstructions, so some sort of thrombus that leads to increased pressure. This could just be increased arterial blood pressure, what we call hypertension. This could be congestive heart failure, specifically right-sided congestive heart failure. That's causing a backup of blood into the venous system, which is going to lead to peripheral, what we call peripheral edema. Okay, so anything that's leading to peripheral edema would increase, or anything that's leading to hypertension and increased hydrostatic capillary pressure is going to lead to edema in the body. Another example would be a decrease in your plasma protein concentration. So decreases in plasma protein concentration, that would be represented by decrease, right, osmotic pressure in the capillaries. So a decrease of pi sub C. So what are some things that can cause a decrease in your plasma protein concentrations? Malnutrition, so not being able to make as many albumins. Liver failure, your liver is what produces your albumins. So if you were in liver failure, this could decrease your osmotic pressure in your capillaries. Kidney failure can also lead to problems in leakage of plasma proteins into your urine. And so all of these things can lead to edema because you don't have as much capillary proteins to absorb that fluid back in. So again, if you were to draw this out here, if we were to sort of do a visual of this, okay, we have filtration, right, fluid going out. But if there were less proteins on the venule side to draw that fluid back in, okay, so less absorption, you're going to have an accumulation of fluid, right? So we get edema out in these tissue spaces because we're not drawing that fluid back in. Protein malnutrition. There's an example of a condition called kwashiorkor. So you may be familiar with kwashiorkor. This is severe protein malnutrition. You will also see not only peripheral edema, but you'll also see abdominal edema. And that abdominal edema has a term. It's known as ascites. And again, this is because in malnutrition, when you are not producing enough of these proteins, you have leakage of fluid into your abdominal cavity, and that can make your abdomen distend. And that's where this term ascites comes from. So malnutrition, liver failure, kidney failure, all reasons for causing edema. And then lastly, an increase in your osmotic pressure in your interstitial fluid. So an increase in pi sub I, or we could even call it IF, interstitial fluid, okay? But increases in tissue protein concentrations. So if there's leakage of proteins into the interstitial spaces, this can lead to edema. So what are some things that cause leakage of plasma proteins? Inflammatory conditions, so inflammation within the body. Allergies can cause leakage of plasma proteins, and that's going to draw more fluid out into those interstitial spaces. Hypothyroidism. In hypothyroidism, we actually leak mucin proteins. So mucin proteins leak into the interstitial spaces, and this results in a condition that we call mixed edema. So sometimes the pathology is just referred to as mixed edema, but this is a hypothyroid condition that can lead to edema in certain places of the body, especially under the eyes. So you'll see sort of fluid accumulation in those orbital spaces. Hyperthyroidism, though, can also lead to edema. In hyperthyroidism, you'll see accumulation behind the eyes and actually will push the eyeballs out. This is known as exophthalmos. And so there's different different medical conditions that can lead to edema taking place. So that was a little bit on capillary dynamics, and also a little bit on then how edema can occur as it relates to capillary dynamics. I hope that helps. Take care.